Good morning, everyone. My name is Simon Pascoe, and I'm from Morbion Hydrogen Energies. On behalf of the Tiger Project partners, I'd like to welcome all of you to this webinar, wherever you're streaming this event from. The topic of this morning's webinar is growing the supply chain for effective, reliable composite blades, tooling, and sensor design for tidal turbines. Next slide, please, Theo. First of all, as you can see from your screens, just to explain to you a little bit how things are going to work this morning, you have a question box at the bottom of your screen where you can ask questions as we go through this session. We'll be monitoring that today for any questions you might have. During our 2-hour session this morning, we have several opportunities to put your questions to our speakers. At the end of the webinar, we'll have 15 minutes to pick up on anything you might want to ask. Any questions we cannot cover today, we'll endeavour to get back to you within the next week. Finally, just to say, the entire event is being recorded as part of the CTech Week event in Brest in Brittany. And we would put this link on our website, the Interreg Tiger website, for those that you cannot stay with us for the 2 hours or your colleagues were unable to be here today. I think that's much of the logistics points which I'd like to raise with you for now. The next slide, please. If you could go back up one slide, sorry, Gio. I would like to introduce you to our panel of speakers we have for you this morning, who will talk to you about their work helping to accelerate reliability and cost efficiency of composites for use in harsh saltwater environments on different types of tidal turbines. We've decided this morning to break this webinar into 2 sessions. The first session will focus on the needs and requirements of tidal turbine developers in relation to composite materials. Needs that can be very different depending on the type of technology that you're looking at. I'm therefore pleased to welcome Erwan Nicola from Sebela, who is the head of research and development at Sebela, whose base is local here, of course, to Brest and Quimper in Brittany. Sebela are developers of gravity-based seabed turbines. And then as a contrast, we'll switch to Minesto, and our colleague Bernd Erik West is joining us from Minesto. They're a developer of a mid-column glider, and Bernd Erik will tell us more about that a little later. Particularly like to welcome Bernd Erik to this session today, who's joining us from the Faroe Islands. So I really do hope our technology stands up and you can hear us clearly. Welcome, Bernd Erik. Sorry that one of our speakers has had to drop out from the Tiger project today, and we had a third technology. We had the floating technology, that of orbital marine. But if you have any questions about that particular technology, we can come back to you after the session with further details. We'll then move on to the second session, where we will focus on cross-sectoral research on composites and their certification for use in these environments, and of course, the lowering the cost of deployment. I'm delighted to welcome Cahor O'Brodig and Jeff Stainer from the University of Edinburgh's Fastblade Structural Composites Research Facility. They will be followed by Peter Davis from Ifremer, based here in Brest, of course, the French Oceanic Research Organization. And we will look at some of the work that Peter's been doing in relation to testing of composites in harsh saltwater environments. Following Peter, we're delighted to welcome Peter Giddings. Peter Giddings is from the UK's National Composite Centre, and he will talk to us about lowering the cost of manufacturing techniques for composites and tooling for tidal technologies. And of course, our final speaker today is Stefan Parbouf. And Stefan is from Bureau Veritas. Welcome, Stefan, who will talk to us about certification and validation of emerging composite materials, bringing us to that critical topic, which is all about what products and services and what technologies we can use for the future. Next slide, please, Theo. But before I start, I'd like to give a little introduction on ourselves, on Morbihan Hybrid Energies. A quick word about the company. We're a new joint venture that's been created between Morbihan Energies and Sibella. We've joined forces in the Tiger project as we're looking to validate a site for 2 pilot turbines situated in fast-moving, shallow water, close to shore, and the national electricity grid that represents a good opportunity to lower the cost of energy production as part of the wider sustainable energy strategy of the Gulf of Morbihan. Our offices are in Vannes, in the south of Brittany. And for those of you in the webinar who are not familiar with Brittany, the Gulf is located in the south of the region. Next slide, please. Here is a map showing the location of the Gulf of Morbihan in relation to the Brittany region on the left. And for those that haven't visited the Gulf, it is an inland sea dotted with numerous islands and outcrops. It's a popular tourist destination, attracting visitors for its beautiful landscapes, covering over 100 square kilometers of the Morbihan County or department, which is given its name. The Breton name, Morbihan, means little sea. It's located in the heart of the regional natural park of the Gulf of Morbihan, which was created in October of 2014. The Gulf is 20 kilometers long, and you can see a picture on the right, the satellite picture on the right, which shows you how extensive this inland sea is from east to west. It opens onto the Bay of Quiberon, known in Breton as Morbraz, the Great Sea or the ocean, through a narrow passage between Loch Mariaker on the north side and Port Navalot on the south side, and the entrance between the two being only 900 meters at its shortest point. Because of this, the tidal cycle is out of sync with the ocean outside, creating significant inertia. For example, when the tide is high in the Bay of Quiberon outside, at the entrance to the Gulf, there is a gap between the time of high water here and the time of high tide 20 kilometers further north and east in the city of Vannes. The high tide in Vannes is therefore 1 hour and 45 minutes after the high tide at Port Navalot. Next slide, please. So today's program, I want to kick off with a very short overview of the Interreg France Channel England Tiger project. I will talk briefly about the Tiger project before introducing you to our panel today. The Tiger Tidal Stream Energizer project, to use its full name, is a project specifically focused on tidal stream energy. It's a 45 million euro project, one of the largest ever awarded by any Interreg program in the European Union. Funded by the Interreg Channel France Channel England program, it is a cross-border collaboration project between partners in the UK and France that is aimed at acceleration, commercialization, and cost reduction around tidal stream energy, with a particular focus on the Channel region. It's seeking to make the Channel a central hub for activity that will help accelerate the take-up of tidal stream energy generation in the European Union. The overall project is led by the organization ORE Catapult. That's the Offshore Renewable Energy Catapult. For those of you that are not aware, the catapults are a UK government initiative set up to bridge the gap between industry and academia to move move more effectively or efficiently address the industry challenges that we face for the future. ORE is a catapult aimed directly at marine renewables and offshore wind, and ORE is ideally suited to collaborative projects such as Tiger, where we are extending the specialist collaboration on a cross-border level on energy generation, on the energy generation challenge that is so vital to the socio-economic development of peripheral regions in Europe today, as we see in the Atlantic-facing regions. Next slide, please. So we have 18 partners in the consortium. We have 6 of Europe's leading tidal technology developers. We have 6 universities, 2 regional development agencies, and a number of industrial partners and research institutions as well. Next slide. Moving on to some of the higher level aims and objectives of the Tiger project, whilst we have a number of partners and sites trying different approaches, the overall aim of the Tiger project is to reduce the cost of tidal stream energy generation to around 150 euros per megawatt hour by 2025. To achieve this, we need to see accelerated volumes of deployment, of testing and first array projects within the Channel region so that we can accelerate learning from them. We have a number of full-scale tidal turbine developers involved in the project, involved in helping the tidal project, and we need to see more deployment of these technologies so that we can accelerate learning and engage with the supply chain to increase volume and scale manufacture. Next slide. This is just a slide showing you the 3 main work packages of the project. As I've mentioned, we have a big focus in this work package 1 on the site development and deployment of offshore testing at sites and all the learning that's associated with that. The second work package focuses on technologies, significant reductions in the levelized costs of energy and the capital costs, focusing on components and equipment and looking at the manufacturing costs of producing those components. On the operational side, there's a big focus on offshore maintenance strategies, operational logistics, the use of real-time data on the reliability of components, and with a focus on the other side of the equation to reduce that levelized cost of energy. Finally, in terms of the third work package, the focus is on commercial considerations. We're looking for the Tiger project to reach out to financiers, to insurers, looking at the scope of increasing project debt into first commercial arrays, reducing the cost of project debt and reducing the equity risk associated with tidal stream technologies. As technologies mature, generating costs fall, so the cost of capital available to the sector shouldn't inhibit its future growth. Next slide. So turning to the tidal sites in the Tiger project, you see we have very good representation in the Tiger project on both sides of the channel, in France and the UK, to stimulate and enable the sector within the Channel region, which we believe has the potential to reach over 4 gigawatts of tidal stream generation in the Channel alone. Here you can see 5 of our tidal sites where the Tiger project is present across the Channel region. We're focused, of course, at Morbihan Energies there with the Morbihan site, but you also see a second site in Brittany, that of Paimpol-Bréhat. The site, of course, in Normandy of Le Raz-Blanchard. Pitec there, of course, up there in the Isle of Wight and the south coast of England. And of course, interests from across the Channel region working at the Ramsey Sound tidal site at St David's Point in west of Wales. The project itself has a target of 8 megawatts of deployment, which would be a big success given the short-term nature of the project and the need to consent and commission these machines. It could lead to further sites and arrays being explored using the knowledge exchanged over the 3-year timeframe of the Tiger project. And I turn now to today's webinar and the context for working with you and talking to you. It's worth pointing out the consortium is working on over 46 different equipment designs for tidal stream energy. And we do not want to do that in isolation. We want to reach out to the supply chain on new optimized components, system modularity, plug and play, so that we can contribute to reducing those costs in the longer term for this type of technology. Next slide. The objective of today, therefore, is to reach out and tell you a little bit more about what we are doing, so you can think about potential collaborative approaches and opportunities within the sector, and of course beyond the sector. I would like to remind all of you that you can also register for regular project updates via the mailing list on our platform. So I think that's about it from my side. What I'd like to do now is I'd like to launch into session 1, and I'd like to introduce our first speaker. You go to the next slide, please, Theo. I'd like to turn to our first speaker, who's Erwan Nicolas, the head of research and development from Sabella, who manages a range of externally funded collaborative projects at the European level and within France. So to kick off the session on the needs and requirements of tidal industry, Erwan, it's over to you. Thank you.
Thank you, Simon. Good morning, everyone. Sabella is a partner of Morbihan Hydro Energy to develop tidal site of Morbihan Gulf. I will present you Sabella society and technology and opportunities for the supply chain at the end. Next, please. So first, I will present the company, the Sabella technology, our first demonstrator detailed project, the presentation and feedbacks, the next generation of composite blades for Sabella, and main project and procurement opportunities. Next. Sabella was created in 2008 with a small machine installed in Brittany, which was the first tidal turbine installed in France during 12 months. It was a 3-meter diameter turbine with a 30 kilowatt production. And in 2015, we installed a detail machine with a 1 megawatt power, which was the first tidal turbine to supply electricity to the French grid. It was installed in Ocean Island in Brittany. We are a SME with 25 employees. We work on EPCI, engineering, procurement, construction, and installation of tidal turbines. We are ISO 9001 certificated. We have a 100% owned subsidiary in Canada, Hydrosab, and an Indonesian consortium. Average turnover of €1 million, and the shareholding structure composed of 25% of industrials, 50% of financial, 20% of founders, and 5% of management. Next. Sabella chosen a differentiated solution for tidal turbine to simplify it in order to increase reliability. We have an horizontal axis turbine with fixed blades and no yaw system in order to improve yield, proven design and ruggedness. We have a low rotation speed, which is marine-like friendly. We have a direct drive generator with permanent magnet, so we have no wearing pack, no gearbox. We have an onboard conversion chain and transformation with complete redundancy, which increases reliability in case of component failure. And we, at the end of the turbine, we can provide power which is directly usable on the grid. And we have a modular architecture, installation on OEM cost reduction. And at the end, we have a gravity-based support structure with ballast weight in order to have a good environmental impact. Next, please. Sabella is working on a complete product family to fit with local site characteristics. We have a range from medium to high power devices, which with a rotor diameter depending on available water depth and a rated power according to marine stream velocity. We are working on machine from 8-meter diameter on 250 kilowatts, which is a machine we work for Morbihan site, and we work also on biggest machine with a 25-meter diameter and 200 kilowatts power. Next. The main advantage we want to work on the standardized subpart to benefit the volume economy and ease of industrialization. And we can work with gravity base, which is the case actually, but also on monopile foundation and having a rated power from 250 kilowatts up to 2 megawatts. Next, please. Now we'll talk about D10 project, which is installed in Ocean Island. So we have an insular RV and autonomous community with 900 inhabitants, powered by 4 diesel groups. The peak consumption is 2 megawatts, and the global consumption is 2 million liters of fuel per year. The Sabella project on this island is made of 3 steps, from the first development in 2015 to the establishment of a tidal array in the passage. The characteristics are 55-meter depth, deep, 2 kilometers off the shore, and up to 4.5 meters per second current velocity. So the step 1 was a D10 machine supported by the French government and Brittany region, a 1 megawatt device of 10-meter rotor diameter. And in 2015, we deployed this machine in the Framber Passage and connected to the electrical network of Ocean Island, a weak and fragile off-grid network. Operation and monitoring of the turbine during 12 months authorized period. So we reach an environmental compatibility and operability assessed during the operations. Next. The D10 machine height is 17 meters. Basement is around 20 meters large and long, and the global weight is 400 tons. The rotation speed is between 5 to 15 RPM, so it's very low. Next, please. Regarding the blade and the feedback on the D10 blade design and manufacturing, for the blade, we choose a symmetrical profile, elliptic one, and a constant chord, so that we can produce energy without turning the machine and pitching the blades. We validate the performances with CFD calculation and tank tests. For the blade manufacturing, we use monolithic carbon fiber composites. The blade was composed by 3 main elements: a spar, the blade shape, and a winglet at the top. The blade was fixed to the hub with a steel flange, and we used 2 processes for the carbon composite, a pre-preg for spar and infusion for blade shape. For monitoring, we have strain gauge linked to data loggers installed on the blade by Ifremer. The state of the art and feedback when we designed this blade was a lack of knowledge on real environmental condition and on the behavior of composites in underwater environments. We also have had an absence of design standards dedicated to tidal devices. And also we use an independent design process for the composite blade and the steel flange. So we had a difficult convergence at the interfaces. Assembly process was not really adapted to a higher manufacturing volume. Next, please. That's why we had a large R&D activity for blade design improvement. So the first step is to optimize the blade shape using a very simple tool based on BMT theory. We validate the performances with CFD and tank test. We also manage a refined measurement campaign and study of environmental condition in from strait, including turbulences. And we also drive an analysis of dedicated standard, which appears in 2015 for load cases definition, ISC, BV, and DNV-GL standards for optimization of safety factors. We also made a characterization of composite behavior in underwater environment with Ifremer. We work on the integration of the blade fixation in the blade root. We use insert in composite, as we can see on the picture. We also work on a new manufacturing process to reduce the blade costs dedicated to tidal needs. And we work on a new monitoring methods using fiber optics inside the carbon composite and crack detection system. Next, please. The next step for the blade design will be the characterization of impact of turbulence on fatigue behavior for composite, the characterization on use of new composite materials, included eco-friendly materials, recyclable and biosourced materials, to define an industrialization process for composite blade manufacturing and integration of monitoring system in composite. The main goals for the next generation is to reduce cost of blades for tidal turbines and to improve reliability of composite blades for tidal turbines. The main project for Sabena, the first one is a project developed within Tiger. The step one is to install two D08 machines of 250 kilowatts power. The project is financed by Interreg Channel Program, a pilot farm of 2 tidal turbines connected to the onshore grid and coupled to hydrogen production units. The commissioning is planned for 2022 with 1 year of experimentation as part of the Tiger project and then an operation for 20 years. Integration into the energy mix of the Gulf region for autonomous and carbon-free production. And for this demonstration, the procurement opportunities are a composite blade design for 8-meter diameter rotor, a composite blade supply for the 2 machines, which will be composed of with 3 blades for each one, and also composite aerodynamic appendices supply, which are made of on V10 machine with a fiberglass composite, sorry, with 2 sets of 2 bulbs. Next, please. For the Marine Girl, the step 2 is to develop the Illong site with a farm of 20 tidal turbines added to the two first one. The commissioning is planned for 2026 and operation for 20 years. The procurement opportunities for this step is composite blade supply, 18 sets of 3 blades, and composite aerodynamic appendices, 18 set of 2 bulbs. For the step 3 is to develop the birder site with 20 new machines connected to the onshore grid also. Commissioning is planned for 2030 for 20 years operation, and procurement opportunities will be 20 sets of 3 blades of composite blades and 20 sets of 2 bulbs of for composite aerodynamic appendices. Next. Another project for Sabara is a commercial phase of the Yushan site. The project is called FAR with 2 tidal turbines, which is a pilot farm. This will be a showcase for the fuel-free island energy model. The project is led by AQO Energy. It will be the final step of Yushan Island energy transition toward a green energy mix. We will have a deployment of 2 tidal turbines, 1 wind turbine, and solar panels and energy storage capacity. Commissioning is planned for 2023 for a 20-year period operation. The procurement opportunity will be a composite blade design for 15-meter diameter rotor, composite blade supply with 2 sets of 3 blades, and composite aerodynamic appendices supply 2 sets of 2 bulbs. This will be the first commercial turbine array in France. The 2 tidal turbine will be of 500 kilowatt each, 1 wind turbine of 900 kilowatt, 500 kilowatt of innovative solar panels solution, and an energy storage of 2 megawatt hour. This will cover around 80% of Yushan needs for energy, with a total power of 2.4 megawatts. Thank you for your attention. If you have any question, don't hesitate to ask on the chat.
Thank you, Erwan. I'll encourage you all to keep asking questions, and we will certainly come back to those after our second turbine developer has spoken. I'd like to turn now to Bernd Erik West. Bernd is the Chief Technology Officer of Ministo since 2017. Bernd Erik has 20 years experience with engineering, concept development, and project management in offshore energy. He's speaking today to us from the Faroe Islands, so I hope the connection holds up, Bernd. And will talk to us about composite needs of his tidal stream glider design. I understand that you'll only be with us for a short period after your presentation until 11 o'clock European time. But so if we have any immediate questions, feel free to put them in the chat as soon as you can, and we'll try and get those to Bernd Erik. And those we cannot answer today, we'll come back to you within the next week. Bernd Erik, it's over to you.
Thank you, Simon. I hope you can hear me fine. As I mentioned, I'm talking to you from the Faroe Islands, where we are about to put this machine into the water. This picture is, in fact, from the Faroe Islands. What you're looking at is a DG100 Ministo tidal kite. And in fact, I don't have a company presentation in my slide material. So I'll run you through it quickly, verbally. What we do is basically fly underwater with with a system that looks like this, tethered to the seabed. And we basically get up to a glide ratio of around 7 or so. I'll get back to some numbers later. So in a 1.6 meter second flow, we will propel this thing forward at roughly 20 knots. That means the system can be much smaller and still produce a lot of energy, or convert a lot of energy. And what's also interesting in this particular picture you have on your screen is that you can see it's actually tied down to the quayside. That underlines perhaps that it's lightweight, because if we don't, it might, I don't think it'll be able to fly perhaps, but it will definitely shift on the quayside. So these systems are light, so which I guess aligns well with the theme of today, which is composites. So our company is a Swedish-based marine energy developer in Gothenburg, Sweden. We're listed on the Stockholm Stock Exchange. I've been around since 2007. We have somewhere around 55 employees distributed on our operations in Sweden and in the UK, where we have a couple of sites. And we have some legal entities here on the Faroes, as well as in Taiwan, where we have some interesting sites. And we do same as Sabella, basically. We do the engineering, the procurement. We manufacture these ourselves, actually, and we also install them and operate them. That's not our plan going forward. The ambition is to become a supplier of power plants to other companies that would then do the site development and operate and basically buy power plants from us. That's our long-term goal. So if we look specifically down to the construction of this type of power plant, basically what you see is tailored to our application. There's the wing, we have a tether in this view, we have the turbine, you can see the rudders, elevators, and parts of the nacelle as well, clearly the struts. None of that, you can't go anywhere and just buy those, because they need to look exactly like this in order to fit. But what's inside of the machine is more or less, there is the occasional exception, but it's more or less standard components. And that's the direction where we would like to go, also considering our composites going forward, or the shape of the kite going forward. But it's been an active decision from our side to use existing off-the-shelf components where we can, and that's actually in some cases driven our development actively in a slightly different direction, just in order to actually benefit from an existing supply chain and a vast selection, basically, of options of different components that goes inside of it. We've also actually moved components from the internals of the kite to shore, because that also makes it not just more service friendly, but also a lot cheaper. So I can, if you go to the next slide then, please. Just to sort of underpin this, I'd like to start with the last line. Is the theme of this is composites, but we're not actually locked onto any material as long as it sort of falls within the other line items here. We make our selection on the LCOE criteria almost without exception. So if it's better to go with steel, we will. But it's also the case that composites in this setting has some benefits that steel don't present. And it's when you look at the numbers, you might fool yourself, because if we say that this machine here moves around about 20 knots, we can then create the geometry or the actual structural components that the kite is made out of. So they're already as good as they can become, coming straight out of the tooling. If we do the pylons to the nacelle in steel, for instance, we probably forced into fitting fairings onto these air, which then adds cost, adds risk of them falling off, and they're composites in the first place. So we try to embed as many functions as we can within the same component. So that's so that statement all can be embedded into all of these 5 here. It's so on the flexibility side, clearly with the composites, there's hardly any limitation at all, to be honest. The problem is, at some point you need to decide the actual physical properties of the composite, and then you buy the part basically. Then flexibility goes down the drain compared to other materials which are easier to machine and deal with, at least on a prototype stage, which we are still. So that adds some onus onto the design and the engineering team to really make sure that we have some flexibility elsewhere to cater for potential constraints than provided by us selecting a given design at some date. Also, what's important is to realize that we need, at least, and we think now for all foreseeable futures, our system to be slightly net buoyant. The way we tow them to site when we install them, and what the system does when in slack water, for instance. It needs to be slightly net buoyant as in total, where composites then clearly has a superior performance relative to most other traditional materials. So, and finally, the corrosion. I'm not going to say that introducing composite just removes the corrosion issue, because you have the mixed material and intersections between when corrosion meets steel, for instance, where you would have other issues than just that material corroding away. But it does help out in total. So these are some of the reasons why we're looking into composites. And today, all of our wings, all of our rudders, all of our pylons, all of our struts to date been made out of composites. And for the DG100, we also did the entire fuselage within the nacelle body in the composite material. And that was an interesting journey, because we wanted it also to be watertight completely, which gave the suppliers some challenges actually. But that means that we can just stick our electronics, a few electronics we have within the actual nacelle body that then is bolted directly to the wing. It's a very easy assembly process. It takes away several other issues, and we're so far happy with that approach. So I think we're going to continue that route. You can go to the next slide, please. So beyond having built various systems, flown them, and every time we bring our frontiers forward, we've also done some other sort of side, I wouldn't call them side activities. They're part of our projects, but then typically they're associated with what we're doing next, or they're associated with our test platform in Portaferry, where we fly slightly smaller systems. So one thing we have been looking at, and we've been extremely successful with so far, was trying out a low-cost tooling option, and how we could structurally design the wing such that it could be much faster to build. And I'm talking now for scales that are maybe 5-6 meters or smaller in wingspan. So to give you an example, we were able, from order to delivery of the test wing to Portaferry, which is a 2.5 meter system, it took 6 weeks from order to delivery, including building the tool and building the wing and transporting it to us. That's so this just opens up another avenue for us, which we're now investigating into how far can we stretch this. And this is an important, this is how I would try to approach my presentation, as to how do we deal with the supply chain in this respect. When there is, so when we have our dialogues inside or outside of ongoing contracts, we really try to understand what's driving the cost on the supplier side, and potentially how we can work together to remove those. So we might not see those necessarily due to the way we have to procure things, being constrained by sort of procurement laws, if you will. So that dialogue is really important, and it adds time to the whole stage, or the whole to the not stage, but the whole process. As suppliers might have different approaches, they might do different techniques. They clearly have different people, different experiences. Somebody may come from like Formula One space programs, other might be focusing on aircrafts or fast-moving or luxury boats for oligarchs and so forth. They have different experiences, and trying to consolidate those is a time-consuming effort. But I think we're doing fine. Another aspect to this is to understand in the prototypes, and if you want to buy 1,000 wings, say, clearly the manufacturing capacity and the logistics, that's going to be sorted. But if we want to have 3 wings built, for instance, we need to understand if there is a typical upper bound of how you would transport those. If the facility sits on the seafront, not a problem. But if you're relying on road transport, those things, you might actually, I wouldn't say we would necessarily add that constraint, but if every single supplier or a vast majority is pointing in that direction, we need to take it into account. Otherwise, it might not even be possible to do it, or extremely expensive. So it's back to the LCOE part of this. Finally, we also would like to use our composite bodies to do more than one thing. So I explained how we manage to make them watertight, but we're also using them to hold different devices for us, or to be an integrated part of how you handle it offshore, so you don't have to add lifting objects or zones. So now it's very slick out of design, but there are features built in that would provide secret functions, if you will, like Easter eggs almost. And we do this not only on composites, we do it throughout. So we've managed now to remove a lot of sensors, because although a sensor isn't necessarily expensive, it will eventually probably, it comes with cables, it comes with penetrations, it comes with potential domino effects. So we're now in a position that we can remove all of our external sensors, we think, and only rely on the ones we really need to have. So we look at, okay, we do have this control unit, what can it do? So it's a general thought or a way of thinking in our organization, I would say. You can go to the next slide, please. Rush quickly through this. I think this is more or less the last one. So if we then go into an actual procurement stage, if we want to buy a 12-meter wing, say, or 2 of those, we need to go out on it with a specification, and we need to follow a certain protocol in order to, at least if we want to claim the money from say, a conglomerate like the Tiger project. That makes it difficult for us, and I would assume for a lot of people in our companies in the same situation, to actually have this engagement up front to make sure that you get all these ideas embedded into your specification to the product you ultimately will receive. And this is one of the major challenges at the moment, because if you go one more slide, next slide, please. So if you have a really large supplier, any component, clearly they will have the ability to put a lot of people and a lot of resources onto helping you out. But we've experienced at least a few years ago that none of those are really interested in looking at 1 or 2 components for us. Yeah, come back when you have 10 to 100 or so. We're seeing that changing a little bit, but it's still an issue. We're sort of in this small to mid-level range of suppliers in terms of capacities, which is good. They're agile, they're interested, but they may not always have this extra capacity on top that you might really want sometimes. Or my dream, of course, is that we make mid-sized, small-sized companies really large by being a part of this journey. But to sum it up, is to get the specification right and to get the supplier inputs, not just from one, but from multiple into the process, and then assigning the contract to companies that have the actual financial capacity to deliver properly, the engineering, the resources and the capacities to not only meet, perhaps even during the process, improve what they would like to deliver to you, and ultimately be able to do volumes later. I would say would be my final words and a summary of where we are on the composite supply chain. So if you have any questions, I'm here to answer for a few more minutes, and then unfortunately I have to run to get one of our kites.
Bernd Erik, thank you very much for your time. Immediate question that's coming in the chat, which I can put to you, is what are your current estimates or levelized cost of energy estimates that you're working to?
I think I'm not 100% exactly what the last number is, but we can revert back. But I'm saying it's what we have seen the last couple of years is that what was a good number in 2015 is a very bad number today. So we've raised our bar considerably, I would say. But I can't say if it's 100 or if it's 70 or 69. I can't really give you a firm up number. I have to revert to Osh on that, I'm afraid.
Okay. Well, thank you for your time this morning. I would really urge you to, with Ocean, to have a look at the stream later on, because there's going to be an interesting second session, I think, addressing just some of those points you talked about in terms of the interest of industrial partners in seeing the scale up rather than the small units. And certainly we'll be interested to hear from some of our speakers in session 2 on this particular issue. But for the time being, Bernd Erik, thank you for joining us.
Thank you.
Could I look to Erwan and Theo just to see if there are any other questions in the chat that we'd like to raise? I think I can see there's a couple of questions coming in which are directed towards you, Erwan.
Yes.
Isabella, can you see these?
Yeah, I will answer the question by Phil Slack about the need we have composite research. I think we are yet working with Ifremer, for example, for composite behavior in underwater environments. So we have a coupons from D10 from, I think, yes, 6 years that are still testing. So we have good idea now from standard composites for that. I think the most critical point would be what was also indicated by Minneso is the manufacturing, because the fact is we have very, very low series actually, and the cost for carbon composite are quite high. The fact is to develop specialized standards to design and manufacture blades for tidal in order to reduce costs and to have in mind that we will probably have medium series to manufacture. Another question we have is about the use of the actual test of biosourced resins. The fact is, when we work on D10 with Ifremer, we also test biosourced fibers, but this was not enough tough for tidal blades. I think we have a lot of things have better in composite materials. We have still, as we are also involved with Ifremer in a real tide project, which is a H2020 project, we will work on coupons for new materials and try to know what can be used for tidal. But there is a lot of work to do from the test to the industrialization for tidal blade for these materials. Another question we have is about the number of blades of Sabalot's machines. You're right, we had previously 6 blades on the D03, the first one on the D10. The fact is, now we are working on 3-bladed machines for 2 reasons. The fact is, the cost, global cost of the rotor. 6 medium blades have a higher price than 3 big blades. That is the first one. And also from all the mounting, assembly of the machine, it's easier to have 3 blades in order to lower the turbine when we make the assembly. So this is less risky for people working on the machine if we have 3 blades. And for marine operation, it is less risky to have 3 blades to manipulate the machine on the vessel.
Thank you, Erwan. We've got a question which is slightly off the topic of composites, but more of a general question, Bernd Eric, about the acoustic noise of these turbines. Maybe you could just quickly reply to that one for me.
Yes, I noted that on the. Are there any limit? No, sorry. Do you have any idea about the underwater noise generated by these turbines? Yes, we do. We've run different, both as a part of the Power Kite, which is a Horizon 2020 project. We've had Queen's University set up measuring noises and also predicting it for our smaller test site in Portaferry. Then on our own tab, we've set up systems to monitor the DG500 in Holyhead, which is a utility scale system, 12-meter wingspan. And we record this data and we can listen in literally to look for various frequencies and find out actually what it is. And that's actually fun, I have to admit, to just try to pinpoint which frequency is this and to set that towards our log files and see where the kite was, what it was doing at that point in time and so forth. So yes, we do. And we also have, in some cases, it's another challenge, which I guess is worth the topic of its own, is to get the environmental consents and licenses in place for operations, which could be really long processes. But some of them might actually force you to, or require you to upfront tell you what this is actually specifically going to result in on that with the machine and the site that you're proposing to use. Or they request you to record and potentially present this material to the authorities. So the short answer is yes. So now I gave you a long one.
Thank you very much. Well, I would like to move on because we're dropping slightly behind time. I'd like to move to session 2 because we're going to move into some fascinating areas about what's emerging in terms of cross-sectoral research in relation to composites, in relation to their certification, and of course the lowering of the costs of deployment through the new technology advances. So I'm delighted to welcome now a double act from the University of Edinburgh's Fast Blade Structural Composites Research Facility in Scotland. I'd like to welcome Professor Gohor Obrodig and Jeff Staynor, who will speak for a short time about the work that they're doing in this area. Gohor is the head of the engineering and chair of materials engineering at the University of Edinburgh. He's the principal investigator for Fast Blade Accelerated Structural Testing Facility, which is the world's first dedicated tidal blade test facility when it was constructed in Rosyth, Fife in Scotland in late 2020. He's also a member of the ETIP Ocean European Union Technology and Innovation Platform for Ocean Energy, and he's a leading expert in fiber reinforced composite materials with interests in manufacturing, testing, modeling of composite materials for renewable energy applications. Jeff, who will complement Cahor's presentation, is a project management professional with a PhD in minimizing embodied energy and carbon. Cahor, it's over to you. Thank you for joining us this morning.
Thank you very much, Simon. I hope everybody can hear me okay.
Yes, we can hear you loud.
Okay, very good. If you could go to the next slide. So thank you very much, Simon, for the very nice introduction. And if we could go to the next slide again. So as Simon said, this is a double act presentation, and actually my colleague Jeff will be doing most of the presentation. So we could go to the next slide again. Yes, so this has been a 3-year journey for us so far, and the entry into service of the facility will not now be until next summer. We've had some delays due to the COVID crisis, but I would like to acknowledge all of our partners, in particularly the University of Edinburgh, who are co-funding the facility along with the EPSRC, which is the UK Research Funding Agency. And I'd especially like to acknowledge Babcock International Group, who are a well-known marine and defence construction and design company. And as Jeff will show in the presentation, we'll be hosting the Fast Blade facility at the Rosyth dockyard. I'd also like to acknowledge all of the partners in the project that have been helping us in design, etc., between OEMs, Offshore Renewable Energy Catapult, various universities, standards bodies, etc. Without them, it would be very difficult. So again, if you go to the next slide, this animation just shows the main features of the Fast Blade facility. As Jeff will show in the presentation, tidal turbine blades have to be fatigue tested hydraulically, and this is quite an expensive process. So the USP of our facility is the use of a new technology called regenerative hydraulics, where the strain energy stored in the blades can actually be recovered in the hydraulic system. So sticking with the theme of reduction of levelized cost of energy, we should be able to test fatigue test facility blades and other structures approximately 8 times faster than a standard hydraulics technology. And with that, I'll hand over to Jess Stainer.
Thank you, Cahor. Okay, can we go to the next slide, please? So Fast Blade will be an innovative structural composites test facility. We are looking to make sure we're capable of testing not just today's blades, but tomorrow's blades. So you'll see here we have 15 meganewton meters in static moment. There's an M missing from that. And then that's the equivalent of 8 double-decker buses hanging about 5 meters away from the route, going up and down every second. And as Simon said, as a project management professional, I've made this a little bit slower and a little bit less efficient, late and more expensive. The University of Edinburgh has put in the extra capital expenditure to make sure that this is ready for the tidal sector, so that we can address the problems of blades as they grow in size and develop. But we're not just limited to blades. We can test anything that fits within a 12 meter by 3 meter by 3 meter box. So aircraft wing boxes, marine structures, anything that is stiff and slender. So going to the next slide, you'll see how a blade is laid out onto the Fast Blade test facility. That loading area will allow us to place hydraulic rams in any position along its bed. This 70-ton box beam reaction plane is designed and developed by Babcock, with a universal adapter plate to take hopefully any of the blades, or we can make the interface plates to go between them. We have a 1,000 liter per minute regenerative pumping system, which is underneath the floor in the grating delivered by Artemis. And the hydraulic cylinders will be placed along the blade at different positions in order to recreate that spatial distribution, load distribution. So the next slide shows where Babcock is and how they have worked with us to come up with a facility design with the 2 overhead cranes for handling these awkward shapes to make sure that the customer experience is good, your blades are handled well and carefully. And the Babcock site is right near road, rail, and sea links. So we're really grateful to Babcock for finding us this location and developing this facility, as you can see in the animation on the bottom left. So going to the next slide, we'll see that we cannot test tidal blades resonantly because they're just too short and stiff. So when we excite them at their natural frequency, that frequency is so high that the internal temperature of the composite increases to the point where the blades may fail due to the testing rather than, or to the temperature inside the blade rather than to the testing itself. So we need to test them hydraulically, but that is typically expensive for conventional hydraulics where 100% of the energy is lost. I said that I made Fastblade less efficient. That's a joke because it was 85% initially. We've done some advanced modeling within the university. We have a handful of students working with us and modeling the system. But Fastblade will use hydraulic systems to put energy into the blade and take it back out. So the next slide gives an example of this, where you have the next slide, please. There we go. So this is where we will be able to take the energy from the pump on the left and move it into the blade on the right. And what happens here is the kinetic energy stored in the blade is transferred into potential energy as spring energy in the blade itself. And then the pumps reverse in mode, where they go from pumping to motoring, and the energy that we've just stored in that blade is passed back through, and the pumps then speed up again. Now, this is a pre-commercial pump. It's never been done before like this, and it will allow us to deliver things 8 times faster than a conventional hydraulic circuit and recover 75% of the energy. So in a 3-month test, the cost of just operating the electrical costs will be much reduced. And it turns out, if we go to the next slide, that tidal blades had a few standards out there, but the IAC didn't. How do you actually design a test for a tidal blade? And this is where Edinburgh University has worked on the IAC committee and a handful of student projects. Peter Nelson come up with load distribution tools. And not only have we designed the facility, but we're making sure that the procedures to test those blades are suitable to ensure that we de-risk the blades prior to deployment. So here you can see 3 hydraulic rams versus 1, providing recommendations to the IAC, which is now out as a technical specification for testing. And the next slide, please. The load simulation, again, finding a hydraulic cylinder capable of exerting those loads, that came from Fox VPS. And the hydraulic cylinders are bespoke in order to handle this reverse flow, which is being captured by the pumps. There are no servo valves in this. A typical hydraulic test will use a servo valve to direct flow. All of the flow control is done in the pumps. So what we can do is take the spatial distribution of loads, as you see in the triangular bottom left, and then decide where to place those hydraulic rams in order to recreate that load that you see on the left. Currently, we're capable of doing that with 4, and we worked within the IEC standard to make sure that it was suitable for tidal industry. Basically, the wind industry has a large gravitational load. Every time the blade goes up and down, the gravitational load switches. That's not the case in tidal because they're mostly neutrally buoyant. So that gravitational load is low. So what we have done is hopefully made it so that one test, one load vector can simulate that tidal blade for 20 years rather than testing flapwise, edgewise, flatwise suction side and edgewise trailing side. So that we've reduced those 4 tests down to 1. The next slide, please. Introducing the loads into these blades, we provide a service for making sure that there is no parasitic load effects. We have a student who is available for a PhD if anybody wants him, Miguel Valdiva. He's done this as part of a research project within his MSc and developing tools for us to make sure that these test designs are suitable so that the failures, or the hopefully no failures, occur in the right position, and again are not parasitic to the fact that we are trying to recreate the complex ocean within a lab environment. And the next slide, please. The instrumentation suite at Fastblade will be dealing with about 500 gigabytes a day. We've worked with National Instruments and Match ID and applied measurements to make sure that we have not only a good suite of instruments, but also the software behind it. Match ID is providing us with the software to do 3D image correlation, which gives us a full strain map of the blade all the way around. This is an example of a 6-meter torsion box, and we were capturing the strain and deflection across the transition in the middle, and we had that on all sides of the blade. And these skills are also, if we go to the next slide, please. All right, sorry, this is the... So I was going to talk about digital skills. We'll come to that. I should note here that Fastblade is not just for tidal blades. Fastblade is also for any equipment, like I said, that fits into the 12-meter box. So here we have mast raising equipment from a submarine. For example, the wing that we saw earlier potentially could be tested on a Fastblade system loaded in the middle. And we encourage developers that as they pull up new designs and they want verification of manufacturing techniques and shapes, we are a reconfigurable and adjustable system. We're not just for tidal blades. As you can see, the universal adaptive plate here is not being used. This is effectively a very long, strong floor. So the next slide shows us how the University of Edinburgh has worked with other developers in their development chain. Fastblade is at the end of this, but we do have the FlowWave test facility for evaluating models, testing at scale, and we have had good luck with developers moving towards full-scale deployment and hopefully have enabled QED, for example, in the top right as part of the Tiger project. And within that, we have a lot of expertise within the University of Edinburgh to help make sure that these designs are de-risked throughout this plan. So the next slide sort of gives an indication, and if you can, okay, the yellow's up, that's great. So here you can see the circle where we start with advanced ocean measurements, Dr. Brian Seller. We can recreate those at scale in the FlowWave tank. Then with scale models, put those devices into the ocean, understand those loads. We can extract that data, wrangle and analyze it, and turn it into a test design for your components. And then on the Fastblade facilities, to complete the loop, we would carry out that test at scale, being able to provide, for example, 20 years worth of in-service loads within only 3 months of testing. At which point, going back to the sea to deploy, having de-risked, potentially gotten certification, more investor confidence. So we have this ability within the University of Edinburgh to complete this chain, and Fastblade is the final tick in the box. So very pleased about that. The next slide, with deployments from 2023, we saw from Sabella, we expect to have some time in Fastblade available, and we would really like to help develop the digital skills in the industry. So we're working with Fife College to develop apprentices, and we'll come up with data and digital skills in an industrial context where the Fastblade facility could be used with existing blades to install sensors, calibrate blades, measure those in the lab, then go up into the classroom and understand how what they've done at scale works on the machines in the lab. And so really, if you're looking for further skills please, Fastblade is part of that, and we can offer that training. And at a level up, going to the next slide, we have engineering skills, where there's 2 doctorates right now with Strathclyde WAMIS program, where it's a wind and marine energy systems, and then David Ingram runs the ID core based around Edinburgh. And really, these are the bee's knees of industrial training and engineering doctorates. So if you're looking for skills, that's what the university really supplies, is good education and skilled engineers. So I hope that's something that you can pick up and take on. So in summary, we've come through, there's a tidal blade test facility, first of its kind. We offer composite blade design, test design, instrumentation training, anything other than a blade for testing, and the full suite of prototype development and digital to engineering doctorate skills. So thank you for listening. I tried to make that a bit fast to catch up and hopefully get back on track. So we're here if you have any questions. Thank you.
Thank you, Jeff. That's great. We're getting a few more questions coming in now from our participants. Just very quickly on the question of how do we contact speakers. Can I recommend that participants use the contacts facility on the Tiger Project website? Our website is interregtiger.com, and I'll show that web link at the end of the presentation. So essentially, we will link you up with any speakers where you have specific questions to pursue. I will come back to questions, I think, afterwards, Jeff and Cora, if that's okay. I want to move on with our next speaker. We're gathering a few questions about composites here, but I think it will be good to take them once we've heard another couple of presentations. I would like to now introduce Dr. Peter Davis, who's been working at IFRIMER, the French Ocean Research Institute, since 1991. His activities within the Marine Structures Laboratory are focused on long-term durability of polymers and composites in the marine environment. His current projects include studies on composite tidal turbines, and very interestingly, synthetic fiber mooring lines for marine renewable energy systems. Peter, the floor is yours.
Okay. Thank you very much. Can you hear me okay?
Yes, loud and clear.
Great. Well, thanks for this opportunity to talk a little bit about some of the work we've been doing at IFRIMER, the French Ocean Research Institute. We have a marine structures group which works on polymer and composite durability and has been doing so for quite a lot of years now. I have 10 minutes to talk about 20 years of research, so I'll go quickly. The question is testing composites in harsh seawater environments. And I guess the first question is, why bother? It's expensive, takes a lot of time. We know that there's a lot of experience of composites in seawater already. Pleasure boats have been sailing for over 30 years at least. Composite wind turbine blades have been cycling for over 20 years, very few fatigue failures. But what we also know is that most small boats are not very highly loaded and not very often used, and they tend to be over-dimensioned, and that we don't cycle wind blades in seawater, or not very often. So it's probably a good idea to check, and this was what we decided to do, I guess, about 10 years ago. Have the next slide, please. So the idea we had was to take a wind turbine blade composite, test it in fatigue dry, then saturate it with seawater and test it again wet. Next slide. And this is the kind of result which we got. So we have the curves, the green, where we have the new material, which was fatigued. We do all our tests in seawater also, but over the test time, the water didn't have time to saturate or get very far in this particular composite, which is a glass epoxy. And then we did the same thing after aging for 3 months, which was the time it needed to get fully saturation, in this case, raising the temperature. And you can see a very big difference between the two curves. So matrix selection matters. We have other materials which we've tested with exactly the same fibers, but with a different resin. where the aged curve saturated was on exactly the same curve as the new dry material. But the bottom line is, one of the first parameters you need to look at is what matrix you're going to use, as the matrix which are used in wind turbine blades are not necessarily the matrix to use in a tidal turbine. Next slide, please. There are other parameters. One of them is fiber coating. So fiber sizing on glass fibers is very important. And this is just a set of three sets of fatigue tests on very similar materials. The only difference is the coating. And you can see we can shift the SN curve from the optimized material here on the right. It can shift it maybe a decade or more left if you don't use an optimized fiber coating. But this is the glass fiber manufacturer's know-how, and this is it's an extreme case to show that it does affect fatigue performance, but in general you can optimize this when you get your reinforcement selected. Next slide, please. And the third parameter is reinforcement architecture, which was something which we hadn't really considered, but I think Erwan showed this slide as well. When we first started on the Sabella project, we looked at a particular fabric and we ran some first fatigue tests, and we were getting very low fatigue performance. These blue plots here. And then when we looked at the damage mechanisms, we could see that the damage was initiating at the weft fibers, which had a very short repeat element. So we looked at other materials, and we looked at a much longer motif, the repeat element, and we got this curve at the top here, which was virtually the same as the curve we were getting for the pre-preg material. So you can get very good performance with carbon reinforcements, but again, you do need to be careful about selecting them to optimize fatigue performance. The next slide, please. And as I'm sure most of you know, manufacturing matters. And one of the key issues we have is upscaling. We can do a lot of tests on small specimens. Our machines are set up for it. So we tend to test specimens in the 3 to 5 millimeter thickness range. But then when you go to 20 millimeters, 30, 40, 50 millimeters, the materials which you very often get are not the same materials as those you've been testing at small scale. And this is just one example of a 20 millimeter thick panel, which we did some work on, again, within the Sabella project to look at the influence of defects. And you can see a very high proportion of porosity. And as soon as you start mechanically loading this, even in static loading, you see a very big drop in performance. So those kind of parameters, you need to have quality control, you need to follow the manufacturer, and you need to be sure that the material that you have on your blade is actually the material you've been testing in your qualification procedures. Next, please. So if we come back to seawater effects, one of the questions is how long it'll take to saturate under real conditions. And there are a number of parameters to account, to use, in fact, to see what your water profile will be. So you can play with water temperature in the laboratory, accelerate your tests by heating up your water. You can play with water composition a little bit. That's going from seawater to deionized or tap water. You can play with coupon geometry. You can play with boundary conditions to get water in more quickly. And then there's mechanical effects, which I'll come back to in a minute. So we have these seawater aging tanks. We've had them for maybe now about 15 years. We have renewable seawater at different temperatures between 4 and 90 degrees. And we can age in these and get the diffusion kinetics. So next slide, please. So this, with the Sabella, we have materials now which have been over 7 years immersed in seawater. These include materials with different thicknesses. We have the materials which are on the Sabella D10 blade. We have the infused materials, pre-preg materials. We have materials at different, I think we go from 2 up to about 11 millimeters in these cases. And we have different temperatures. And that has given us a really big database of immersion aging for these kind of materials. So these are just some examples on the top left of some curves. We have curves for a 40-degree immersion here. The 25-degree immersion is pretty similar for 4.5 millimeter thick samples. We're coming to a fairly stable saturation level. Even after here, we're at about 7 years. And then here we have accelerated tests at 60 degrees, which are very similar up to probably 2 or 3 years. And then afterwards, we get another phenomenon, which is due to a degradation mechanism in the resin. And this gives us an idea of the lifetime of this particular composite. And so from these kind of curves, we can get information on the diffusion coefficients, and these allow us to then calculate the water profiles through a blade thickness. This is an example from PhD work by Nicolas Toile, where we can then get a water profile. And once we've got a water profile in the structure, we can start to look at what the water is doing, relating the water presence to degradation mechanisms, and we have a basis for constructing a lifetime prediction model. Next, please. One question which is often asked is, okay, you do a lot of these tests, you do them on small coupons and you do them uncoated. So what happens when you put a coating onto your composite? That's surely going to stop water ingress. So in fact, we developed single phase seawater exposure tests to look at this. You can see on the left here the setup. So we have the coupon here. There's an opening in a test tank, and inside the test tank there's seawater. So it's exposed, in fact, just one side of the specimen. So we're not worried then about edge effects, and we can just look at how the coating we're putting here is affecting the water ingress into the material. And this is an example on the right for a sandwich material. So we have on the bottom, we have the material with the gel coat, and we're very close to zero. We have very little material getting in, although we do have some. And without the gel coat, we have probably going up to a couple of %, and we start to get some degradation. So coatings can be efficient. We've looked at gel coats, but also anti-fouling paints, erosion coatings. There's a range of layers which you can add to the surface of your blade. But the problem is while they do slow down water ingress, they don't stop it completely, and they can be damaged. So that if you then get the removal of the coating, you get back to your worst case, which is what we're looking at in most of our tests. Next slide, please. And then the other point to underline is that in reality, we can put materials in water, look at how they degrade. We can also look at the mechanical behavior. But in reality, these are acting together. So we have water ingress, permanent immersion, and we have mechanical stresses which are constant or variable throughout the lifetime. And the rate of diffusion of the water also depends on the stress, the stress levels. So if you get higher stresses, you tend to accelerate water ingress. And the mechanical properties depend on the amount of water in the material. So they're tending to degrade, and as they degrade, you also get damage introduced, which can also accelerate water ingress, and you can get a kind of at some point you can reach an auto-accelerated degradation. Just to give an example of how the water ingress affects the damage and how this can then affect the water ingress, on the next slide. Next, please. Thank you. So this is a set of data for a carbon epoxy material, quasi-isotropic, which was immersed. And what we're looking at is the amount of crack density. So this is essentially the amount of damage on the y-axis, and we have the applied stress here. And so with the dry material, we were going up to about 550 MPa before we saw some cracks appearing. And then for the saturated material, which is the blue triangles here, this curve shifts to the left, and the damage initiation threshold has gone from about 550 to about 300 MPa. And more important is that saturation is one parameter. We have water present throughout the material, but if you continue the test and leave it for longer times, the material can degrade further. And these are the green points here. We had, after 1, 2, 3 months of saturated state, and you get an even lower value around 250 MPa. So as this damage goes into the material, the water ingress parameters also get affected, and we get a continuing drop in properties. Okay, next. So that was a very quick overview. I just put a few conclusions. I think one is that you can't assume that the good fatigue properties of wind turbine composites are applicable to tidal turbine blade applications. So I think that is something which we were concerned about, although clearly when you start looking at these applications, you go for a material which has good fatigue properties. But the marine environment is very severe, and water resistance is clearly top of the list of the parameters required. That's affected by the matrix, by fiber coatings. Reinforcement details can also affect the long-term durability. Next, please. And the conclusion we've come to is that, which is perhaps we're not completely unbiased on this, is that appropriate testing increases the confidence in the long-term behavior, can allow us to get to lower safety factors and resulting to lower cost. And this is something which we're studying at the moment in the real-tide projects. Erwan mentioned that. We're working still with Sabelo in this project, and also with the University of Edinburgh and a number of other partners. I think the Bureau Veritas, who's leading the project, will say more about this in a minute. There are different aspects within that project. There's an aspect, structural testing. There's a lot of hydrodynamic testing and also measurements at sea. But we also have a section which is on alternative materials, which we're working on at the moment. And I think some of the questions I saw on the from people listening were about these alternative materials. So the idea was to fully characterize in all the static properties which we need for design, and the fatigue behavior of a carbon epoxy material, which is the material we're using for D10. Glass epoxy material with the same epoxy, just changing the fibers, and looking at how that can behave, and which will allow us to dimension the blade by using glass. There are some tidal turbine blades do use glass, but generally the shorter ones. And then the alternative materials for the carbon, we're looking at a carbon polyamide, a polyamide 6, which is an interesting material and which has some capacity for recycling. And then for the glass material, we're looking at a glass polypropylene, again, a thermoplastic which can be recycled, and also an acrylic with flax fibers. So we have essentially alternative materials for the carbon epoxy and the glass epoxy. And we've been doing a lot of aging on those materials, looking at how aging affects fatigue performance. And the idea is to introduce that into the design loop to see what dimensions would be needed if they're modified or not with these alternative materials, which have at least potentially a much lower environmental impact. Okay, so I think that is all I have to say. So I'll give the floor back to Simon.
Thank you, Peter. Excellent. We've got some really interesting questions actually coming into us now. The first question for you, Peter. It's: have you been able to test the effect on test crack propagation and its effects on things like water intake, mechanical properties, etc.?
Okay. In fact, we had another PhD which finished at the end of last year. It was Antoine Le Guen-Geoffroy, who worked on looking at aging and delamination. And so we did a lot of, he did a lot of tests under different modes of loading of the effect of moisture on delaminations and how they propagate. So we have he looked at a carbon epoxy. His application was for composite propellers, but a lot of the questions we're asking for those are very similar to the questions for the tidal turbine blades. So yes, we have looked at delaminations. That's one of the types of defects. I know there's clearly a lot of others. We have done some work with porosity, although not always on purpose. So we have some data on that as well, but it's clearly a very big subject, and I think it's something which we're still working on, and we have another PhD student who's looking at some other aspects of that.
Can you hear me okay?
No, well, yes, I can now.
I've broken up, sorry. I've got a question for Jeff at Fastblade. How do you evaluate the fatigue induced following a long fatigue test? Do you use integrated sensors? And have you already considered X tomography?
Okay, so we haven't considered X tomography yet, but the definition of a failed blade is a reduction in stiffness by 10% in the IEC standards. So as we monitor with strain or DIC and pick up that change in stiffness, we can identify a blade failure.
Okay, thank you very much. I want to move on if I can, because we're falling slightly behind time. I'm delighted now to bring in Pete Giddings from the UK's National Composite Centre, who will talk to us about the lowering cost of manufacturing techniques for composites and tooling for tidal. Pete's a chief engineer for energy at the National Composite Centre. It's one of the other catapults, as we described earlier, with ORE in the UK, and I would like to hand over immediately to Pete to tell us a little bit more about what they're doing in this area. Pete, the floor is yours.
Thank you, Simon. So good morning, everybody. I am going to talk to you about how to lower the cost of manufacturing, but I'm not going to talk in detail about the techniques and the tooling. Actually, I'm going to tie in with some of the messages from colleagues at Fastblade and Iframa and touch on some of the challenges that both Sabella and colleague Minesto mentioned around how to design for manufacturing and still create robust product, even with a low cost solution. So can I have a slide, please? So I'm going to touch on why you need to consider low cost at low volume and what's unique about that. And really that's our challenge at the minute. I'm going to describe the certification challenges of lower cost solutions and just highlight two key enablers which are really important at this stage in an industry's development. You're at a demonstration phase, getting product in the water for the first time, and I really want to highlight something we think could really help with that. Can I have a slide? So you're all really familiar with the need to minimize capital, minimize labor rates, and maximize the profit at the gate. So essentially your margin as it leaves the factory. The things we also need to consider are that you increase your labor and material waste, you lower the repeatability of product leaving. And as a result, you often, when at mass production, lower the profitability through the life of the product. Higher MRO, more failures, and that's something that right now can hurt your credibility, but later will absolutely hurt your bottom line. So the balance between a process cost and process repeatability and reliability is something that we need to consider as volumes increase. So I can have a slide. So where much of the wind turbine industry is, and I think a proportion of the tidal turbine industry is in hand layup, and something which we will need to consider later down the line, probably not for now, is automation, and so tick through, which will increase reliability and allow you to execute your designs more faithfully. But crucially, we need to be thinking about those more automated processes now, so that as you certify a design, it's already suitable for automation. So it's manufacturable in a rate compliant way. And whatever solutions we choose, you need to build confidence that it's faithfully executing your design. So Peter from Iframa nicely describe the impact of manufacturing defects, and those are directly tied to how readily manufacturable your product is. So I can have a slide. You'll all recognize the two bell curves I'm going to show, but essentially this is the challenge in certification. You have a distribution of loads that your product will see in service, and Fastblade is doing a fantastic job of characterizing those loads and helping you replicate them. And then it is our task as manufacturers and designers to create the right-hand curve there, which is the design resistance. So this is the distribution of strength that your product has. So on a good day, you'll manufacture a blade which is on the right-hand edge of this curve. On a Friday afternoon, when the stars do not align, you'll manufacture a blade on the left-hand side. But for demonstrator products, you need to have a robust and comfortable design margin. So your characteristic blade, a typical blade that comes out, needs to be well above your characteristic load. So the red line needs to be to the right of the green line in simplistic terms. And our colleague at Bureau Veritas will be able to give a bit more detail on how that's done. Next slide. For a lower cost process, and this is something we've seen as aerospace transition to lower processes, as automotive bring in composites into their manufacturing, and in wind turbines for a good long time now. We don't have such tight distributions of resistance. So our results are more variable. That's a broader curve. And even for the same design intent, you have more blades that are at the lower end of your design requirement. And you can have the red line moving to the left of the green line. So in other words, there is a higher probability of design failures. So your product goes into the sea and you experience failures, and that is really damaging to an early stage industry. What we really need to work on is helping you as an industry and your supply chain create reliable products so that your design intent is realized and you don't end up eroding design margins. So can I have a slide? So there are two main enablers that we at the National Composite Centre see, and these are two things that have really helped adjacent industries kind of adopt lower cost processes with more confidence. One is design for inspection, and taking the results of inspection and using them to drive design. So that means we need to understand the detectable defect sizes. Many tidal products are very thick in section, they might have complex assemblies, and that can have impacts on what size of defect you can detect. Now, for robust designs, and for 20 years in a harsh environment with severe material degradation, you definitely do want to be targeting robust designs. You need to have a good understanding of how your smallest detectable defect will impact your product. Because if you can't detect it, you can't mitigate for it, and that can increase the risk of failure. We also need to help you, and I think there's some good work done already, but there are some improvements in the assemblies that can be done to help make those features more inspectable and to reduce the inspection cost. And those enable you to put product in service, even if it's manufactured in a lower cost process with low reliability, because you have confidence that that particular example of your product is faithfully representing your design and therefore reduces the probability of failure. That reduces your over design. So you don't have to put more material in to make up for mistakes you don't know about. And then in design for manufacture, and this was something that Minesto specifically highlighted as something that they weren't able to do because of the stage of investment they're at. And I think this is common across many of the manufacturers where there's a significant proportion of public funding. You need to have control of your manufacturing process so that you can represent it in your design. It reduces manufacturing complexity and the risk associated with manufacturing, but it also allows you to select different tooling strategies or ultimately automation strategies that reduce capital cost. And ultimately, it reduces product variability massively. And that allows you to reduce the underperformance. So you enable your supply chain and ultimately your own manufacturing to achieve design intent. So I can have a slide. And that moves us away from this broad variable distribution of product to a much tighter distribution, say tick, that gets you back to a position where you have a design which was always intended to be compliant, which is faithfully executed because you've worked at the design stage to enable it to be manufactured well. And you've worked at the design stage to be able to inspect it, to check that it has gone the way you wanted. And those really massively increase your design reliability. Now, other industries can take a high cost, high reliability process route, but to hit your LCOE targets, that doesn't support the tidal industry's trajectory. So what we see is a really good opportunity, slide, to be able to work for design for inspection. So we get some tidal specific guidelines on what is inspectable, and to be able to help you implement those learnings back in the design process so that you and your supply chain have confidence that the work they do is implementable. So tech. And as you work, as we, hopefully we, work forward as part of Tiger and in other programs, as you start to look at design for manufacture in new product variants, you can really start to build up much more reliability and the ability to execute what you plan to. So to take those really great learnings from Fastblade on what loads are present, to apply the learning around materials degradation from Iframer, and manufacture with an understanding of the reliability of your processes. And that really is the critical next step that helps you get product in the water with confidence and for it to come out after a successful validation. And that's the key to unlocking those higher volumes. So I really hope that we can discuss and I can answer any questions around design for inspection and design for manufacture. And I just want to thank you for your attention. So any questions, please?
Pete, what I'll do, if that's okay with you, is given time, I want to move on to Stefan. We'll take questions at the end then on both presentations because we're moving seamlessly really into our final speaker. Stefan Parbouf is from Bureau Veritas, and he was going to talk to us about certification and validation.
Yes, can you hear me?
Of emerging technologies. Stefan, if you can hear me, the floor is yours.
Okay, thank you, Simon, for the introduction. So I will speak about the two research projects, RedTide and NEVEF, where we are developing fatigue methodology for composite blade. So briefly, a short introduction of Bureau Veritas. So Bureau Veritas is a world leader in testing, inspection, and certification. We are organized in different divisions, such as industry, construction, food, consumer products, marine and offshore, etc. And so in marine and offshore, our role is to verify the conformity of ship and offshore units to classification rules and standards in order to ensure a high level of safety. So in the composite material section, we are involved in a dozen of research projects concerning adhesive, large vessel in composite, composite propeller, patch repair, and also marine renewable energy. So the objective of this section is to develop and to improve existing rules for the application of composite material in the marine and offshore industries. So next slide. So I will start by speaking about RedTide. So RedTide is a European research project in the H2020 program. Bureau Veritas is the coordinator of this project, started in 2018, and the total budget of the project is 5 million euros. So the objective of RedTide is to identify the main failure cause of tidal turbine and to provide a step change in the design of blades and also for the power takeoff system, by adapting them more accurately to the complex environmental tidal conditions. So that means that we should have a full understanding about the reliability issues of existing tidal blades, that we have modelization of the tidal turbine and its environment in realistic conditions. And it's also important to develop an advanced monitoring technology and strategies, and also an associated condition-based maintenance. So next slide. In order to have a full understanding about the environmental conditions, a large campaign of measurement has been carried out by University of Edinburgh, with different sensor installed on the D10 site, that is a Sabella turbine. in Brittany. And a lot of modelization of the site has been performed by University of Edinburgh also, in order to modelize the site and to be able to evaluate the different environmental conditions in the different weather. So from this measurement and from this modelization, so now we should apply this for the mechanical system. So if you go to next slide, we have developed within Riptide a new tool named Starblade, that it's a tool for the computation of forces on the tidal turbine blades. So the tool is based on the blade element momentum theory, and some improvement have been considered during the development in order to consider the realistic and dynamic flows. And the tool is able to perform fast computation in compared to CFD solver. So it's less accurate, but for the fatigue evaluation and for the loading of blade concerning fatigue, it's a faster solution. So now, next slide, please. So concerning the fatigue methodology, it's important to remind that the fatigue and the different complexity of the phenomenon. So we have complex loads due to a dynamic flow environment and due to flow modification by the rotation of the turbine. It's a complex material, so composite, it's complex due to a multi-layers material, anisotropic and non-homogeneous. And also the fatigue, it's a complex mechanism and it's a non-linear phenomenon. So in order to address this complexity, in next slide, we have developed a methodology in different steps by considering the loads, the material, and the fatigue itself. For the loads, we are based on the NI603, that is the big guidance node for tidal turbine. And the force distribution is computed with Starblade. For the material, it's a ply-by-ply approach by using the freeware, the BV freeware composite. And for the fatigue, we will use load distribution for the stresses. The SN curve is based on different tests that we have performed within Riptide. And the damage is evaluated by the Miller sum, leading to the total fatigue damage by the cumulative damage calculation. So now, in order to validate this methodology, we have performed some tests in the next slide. So a full-scale test will be performed in Ifremer facilities. So on the left, you can see the metallic bench assembled in Ifremer in Brest. And so we will perform static and some cyclic tests on the full-scale blade. A finite element model has been also performed in order to compare and correlate the results that we have with testing and the finite element model. The finite element model allows also to have the stresses distribution along the blade, and it allows also to determine the position of the instrumentation. As you can see here, we have a lot of strain gauge, optical fiber, accelerometer, etc. Will be installed along the blade in order to monitor the test and to be able to evaluate the behavior of the blade and to compare with the finite element model. So now I would like to speak about the MEVEF project. So MEVEF is a French research project partially funded by ANR. It started in 2018. And the objective of the MEVEF project is to treat the behavior of composite structure in fatigue and also by coupling with edging. The MEVEF project will propose some predictive model, and at the end we will be able to develop or to complete the existing rules that we have. So in the next slide, So for the loading of the blade, we have use again star blade, and we have defined a fatigue spectrum based also on the installation site of a generic turbine. And the first step was to perform some coupon test in air and also in seawater. Next slide. Next again. And so by this system, we will be able to evaluate the influence on the seawater of the mechanical properties, and we will be able to define some SN curve in dry situation and also at the edging stage. Next slide, please. So here you can see model scale of the blade. So some tests are ongoing in tensile facilities on the model scale. So static tests have been performed for the moment, and we will perform fatigue test in a few weeks. The fatigue test have been also compared with the finite element model and the predictive model, and an extrapolation for a full-scale model has been done in order to evaluate the possibility to perform a model scale test in comparison to full scale, that it's more expensive and it's longer than model scale. So it's the same fatigue methodologies that we have developed in real-time, and we will apply the same thing in order to assess the fatigue life of this tidal blade. So now in conclusion, in the next slide, thanks to these two research projects, real-time and MEVEF, thanks to the results that we obtained with the coupon, but also with the full scale and the model scale test in static and in dynamic. By comparison and extrapolation with the simulation, we will be able to validate the fatigue methodology that we have developed. And the objective is to implement this fatigue methodology in the PV guidance note NI603 to help designer to develop reliable system for the future. So thank you for your attention, and I will try to answer your question if you have.
Thank you, Stefan. Very, very much appreciated. Jeff, would you like to ask Stefan your question about the real-time project?
Yeah, Stefan, I was just curious on the magnitude of the loads and the number of cycles that you were applying in the real-time project. I think I just saw there 300,000 cycles.
Yeah, it's a very, very low number of cycles, so it's mainly a static test. And so some cyclic tests will be performed, but the objective is to go up to the failure of the blade in static and to confirm the safety coefficient that we have applied for this structure. So it's a low cycle that we will perform because it's not the main objective of this test.
Okay, thank you.
And Erwan, I have a question from Erwan Sabella for Stefan as well.
Yes, Stefan, just a question regarding the fatigue consideration and standards. Do you plan to update your NI 603 soon with that, or to refer to a new standard from IEC?
No, we hope to update the NI 603 soon. Probably in 2021, that we will have a new issue of the document by considering the fatigue, but also we will update the safety coefficient for composite material because we have been involved in other research projects recently, and so we have new information now concerning the behavior of composite, and we would like to have an update not only for the fatigue, but for the composite section of the NI603.
Okay, thank you.
I'm also aware of another question which is coming in, which maybe I can direct towards Pete Giddings in the first instance, and possibly Peter Davis. We're being asked the question about the recyclability of composites used in turbine blades. I'm aware of the Zebra project, which the Institute Jules Verne is leading, but maybe you've got other information both on the UK side and on the French side, which could be useful to the participant who's asking this question.
Yeah, absolutely. So there's a lot of interest around recyclability of traditional thermosetting composites. So the Zebra project is actually using an infused thermoplastic to replace thermosettings. So it's an infused PMMA. With more traditional systems like epoxy, there are limited ways to recycle those at present. So you can recover fibers through pyrolysis. There are some limited options for solvolysis, so chemical recovery. And colleagues from a few industrial firms commercializing those. One of the biggest drives that we as the centre have, and we have 2 initiatives that are focused around sustainability, is around identifying value chains for recyclate from composite. So how you can recycle end-of-life components and maintain the value in the fibres and, where possible, the resin. For current generation epoxies, for old generation polyesters, that's really challenging, to be completely open. Many of the current routes are around cutting up the product and reusing those composites. Explicitly recycling materials like current generation epoxies and polyesters is not really something the industry has a great answer to. And that's why we at the centre are working on 2 initiatives to help generate plausible routes that aren't simply energy recovery through burning. One of the things we see in wind, and we're helping to make that happen, is a move towards more recyclable materials. So Simon, you mentioned the Zebra project. There are also other projects and other materials that you can use which are more readily recyclable. So PMMA is one. The nylon that Peter from Iframa mentioned is another good candidate. But that's a material change, and with it comes process change. So if recyclability is a big objective, and to be clear, for all of your businesses, you need to be thinking about that as end-of-life considerations will almost certainly be regulated in the coming years. Then we need to be taking that information in now and starting to think about design for dismantleability, design for those new material systems as well. So it's absolutely a very hot topic, and I'd encourage anyone to get in touch, because we have a couple of initiatives that are already in train, and we'd be very keen to extend those to tidal applications.
Aware of this issue, Pete, from working with the Port of Ostend in the renewable energy offshore base, because they're on their 5th generation of wind turbines, and it's becoming a major issue in the southern North Sea, as the 1st generation turbines need to be brought ashore essentially. So what do you do with them? And of course, anything that can help the circular nature of this economy would be very beneficial in the longer term, and something potentially tidal can learn from. I think from my side, we've got one more question. I think we've got coming in from Tio about blade shape influencing composite material selection. You know, is there a chance that all turbines will end up using the same composite materials, or is it always going to be, there's always going to be a mixed market here? Jeff, would you like to try to tackle that one?
So the shapes of blades and their materials, is Cahir online? Is our composite design? I think after 11 o'clock, Cahir will have possibly gone.
I'm here, Jeff. Yeah, I mean, you'd want a crystal ball for that one, to be honest. I think we're just at such an early stage in the design process that we really don't know. If you look at the much more mature wind turbine blade market, you know, there still are a number of families of resins. Some companies still using polyesters. There's glass fiber, there's carbon fiber, there's epoxy being the mainstay. I think in the tidal industry, because of the size of the structures, there is an opportunity to be more innovative in terms of materials. But I would think that we're a number of years off any kind of convergence in terms of materials.
Thank you, Dora. Well, we've run out of time, unfortunately, everybody. I would like to wind up the workshop here today at CTEC Week. I'd like to thank all of our speakers for making time to be with us today online. I'd like to thank the team at CTEC Week for their help in getting us online. And today, of course, notwithstanding the challenges that a major conference like this is facing right in the middle of a global pandemic. I'd like to thank colleagues at the ORE Catapult, particularly Theo for his support, of course, Erwan at Sevilla, and colleagues at Morbihan Energies who have helped pull together this work today. And finally, to you, the participants, I'd like to thank you for participating and for your contributions. If you want to link up with us, go to the Tiger website, interregtiger.com. You will find a contact page there. You can sign up to our mailing list, distribution list, to keep in touch with the project as it develops. Finally, I'd like to say, obviously with CTEC Week, there is continued functionality in the exhibition, which you can explore, and certainly the B2B functionality. So if you're looking for new project partners, you're looking for contacts, use the B2B function that's available online in the virtual CTEC Week website. It's an incredible effort that's been made to get this whole conference online, and it's a great pleasure to have been a part of this with you all today. So from that point, I would like to thank you all for participating. I'd like to wish you a nice day and thank you for your time. Goodbye.